Welcome to our video lectures on NPTEL on DC microgrid and the control system. Today we shall continue with the previous lecture, that was the control of the vector control of the voltage source converter. We will talk about the left out aspect of this DC to DC converter first. So, that is the control of the power. So, that ultimately you got a measured power, you got a reference power, and we require to feed the reference power, and for this reason you control the PI controller, and thus you got the ID ref and voltage has to be fed. And here also you measure the DC power, what you require in the DC power in the load side, and it may be it is not at all the unidirectional, it may be bidirectional. You can, if you have a power surplus in the microgrid, you can feed back the power to the grid. So, you have to check it. So, the DC measurement and fall also will come into the picture, and this is called these two entities are wholly called the active power handling or the active channel, and ultimately you can switch over to this mode whether you are going into the DC power control or the grid power control. Generally it is in islanding mode you go for it, and in a grid connected mode you go for this power control. And thereafter you may have a sag or swell, and thus but you require to maintain the voltage into the rectified DC output voltage, because when you have a sag, what essentially you will have, your DC link voltage will come down and you require to pump the DC link voltage, and that will be your activity, and then this PI controller comes and ultimately that will be boosted by the taking the extra reactive power. And also you cannot allow when it may be reverse operation also, once you are converting to the DC to AC, we have a surplus of the power, you have to inject a power as given by the grid code. So, you require to control the, when your voltage is healthy generally, then only you will allow, then only you can afford to do that. Otherwise, if your voltage is not healthy, then of course you cannot control your reactive power flow, because ultimately your investigations, your investment will be to maintain the DC link voltage, and thus while in case of the voltage disturbance in the AC side, you cannot maintain the reactive power mostly. But assuming that this is healthy, and you can control the reactive power flow from the AC side. So, the outer control include active and the reactive power loop as shown in the figure 5. Please recall that it is when I am following the same notations of my previous class. For this reason this figure has become 5, previous figure was 4 in my previous class. The outer active power loop regulates the active power or the DC voltage level by calculating the proper D axis or the real axis current by the PI controller, and also the reactive power loop sets as the Q axis currents to control the reactive power of the AC voltage amplitude at the point of PCC. Now, essentially these are the expressions of the real and the reactive power. The active power control equations and the reactive power equation in the DQ frame has been written. So, you will have a VD ID plus VQ IQ are the real power, and similarly you have the reactive power, that is the cross term VQ ID minus VD IQ, and note that this D axis is aligned with any of the phase, for example A phase. So, we can say that if in case of you are feeding essentially if you are feeding a unity power factor, sometimes we prefer to do that, then EQ will be 0, and thus what happen, your survival term will be essentially, because if EQ is 0 then VQ will be 0, your VD into ID and the Q will be minus VQ into IQ, VD into IQ, sorry. So, based on this assumption, that is a unity power factor operation, please mind that, otherwise EQ will be present in terms of the PQ. And based on this 4 and 5, the current in the D axis can be employed to control the active and the reactive power respectively. So, you can see that only the current is sufficient to control. The voltage controller is intended to regulate the amplitude of the voltage at the PCC. So, that is something once you have a voltage disturbance sags and swell, that comes into the picture. Similarly, control of the AC voltage carried out by modifying the Q axis current. So, if you terminate a load with the capacitor, your voltage, terminal voltage will swell up, as simple as that, and thus you require to change the Q axis current. So, sagging or swelling can be controlled by controlling the Q axis current, but in normal healthy condition this is not touched. To maintain the DC bus voltage at its reference value, the active power exchanged within the AC grid must be properly regulated. And please understand, I have discussed classes because there are two issues, because power comes with the 2 cos omega t by 2. So, there will be a average power, and within that there will be a double frequency oscillation, but over a period of time this average value becomes 0. But problem lies instantaneously that power required to be fed, because if you are feeding a resistive load, then if power then when voltage and current both at its peak, positive or negative peak, whatever it may be, then you are consuming maximum amount of the power. When it is 0 crossing, voltage and current both, then also then what will happen? You have a least power. So, average power may be something, but you are varying this power, and for this reason this exchange of this power properly required to be regulated. So, that ripple in the DC will be low. That is something is a very important aspect of the microgrid control. Hence, the modifications of the D axis current ID allow us to control the voltage within the permissible limits. One of the most important component of the voltage source, now we shall go by calculations of those entities, how you will calculate the value of the capacitor, value of the inductor, and of course, rating of the switches, this also comes into the picture. So, one of the most important component of the voltage source converter is that the DC link capacitor, and how we will calculate the value of the capacitor. This capacitor are used to limit the ripples, as I told you, and DC side of the voltage source converter, and therefore minimizes the DC voltage variation, which can be cause significant change of the converter load. Because why there is a DC ripple? So, since it is a 3 phase, you have this kind of DC ripple, 6 pulse, and this would have a very big problem in case of a diode based rectifier. You know that for a single phase you have this kind of waveform. Ultimately, this point of time you do not transmit any power when voltage and current both are 0, and here voltage and current at its peak, it is a negative peak, you send the maximum amount of power, and to balance it you have the capacitor. Since it is a 3 phase system, so you have a less ripple because it does not cross the 0 crossing, because another phase comes into the pictures, and thus what happen, to balance, to smooth out this capacitor, you require to put the smooth out the the smooth out this voltage ripple, we require to put the capacitor. Accordingly, it is necessary to calculate the proper value. So, we come into the necessity of the requirement of the capacitor. Another issue is that how can you calculate the what actually its value would be. The proper value of this capacitors, and so that it can operate beautifully, it can operate as you desire. Now, DC link capacitor can be calculated by the following expressions, that is CDC, that is the value of the capacitor. Essentially, it will be given by the power handling capability of the converter. If it is a 10 kilowatt converter, rating of this power is 10 kilowatt. Then this, what is the voltage level you are intend to maintain. Say if you are 3-phase 3-wire system, you are rectifying it, voltage will be around 600 volt, 440 volt line, and so you are maintaining little bit of higher, maybe you are maintaining at a 750 volt. So, that voltage will come, and the sigma and omega LP are the term, that is the breakover frequency of the VSC of the low pass filters. Once you design it, generally we set this value around 10 to 20 times of less than the switching frequency. If you are switching the converter at, please understand, this is not the frequency 50 hertz or 60 hertz, it is a high frequency operation. So, it is the, we have a PI controller and that has its cutoff frequency. That cutoff frequency we require to consider, and generally if you are switching at 10 kilowatts this converter, it is better to keep this cutoff frequency around 1 kilohertz or 500 hertz. And generally there is a damping factor. So, damping factor is 1 by root 2, and this delta n is the maximum desirable ripple. So, what is the amount of the ripple you can consider? If it is 2%, then this value will be 0.02, if it is a 5%, this will be the 0.05 and so on. Accordingly, size will increase or decrease. So, this is the expressions of the capacitor that you require. DC microgrid consists of number of terminal to achieve the certain functions, which are power generations, grid connections, energy storage and the power consumption. See, these are the few entities that we require to consider. The DC capacitor which help to maintain the system voltage are located at each of the terminals. So, that is something we require to keep in mind, that DC capacitor which maintains the DC bus voltage are located at each of the terminal. The DC lines are set to connect every terminal to form the DC network. DC microgrid terminal can be categorized into the 4 basic types in terms of their functions. They are grid connections, power generation, load consumptions and the energy storage. So, once you are converting, there is a bidirectional DC to DC converter, DC AC converter or AC DC converter, that is the grid connections. Power generation, it can be solar. Load consumption, you may have a loads point that is not bidirectional or bidirectional, and also the energy storage, mostly battery. So, these are the 4 terminal you will be having, and thereafter the terminals in terms of the contributions, the system operation stability can be further categorized into the 2 groups, which are named as a power terminal, like this derivation is taken from the power flow model in the a power system, that you got a slack bus and you got a voltage bus and all those things, and the similar term will be there, that is the power terminal and the slack terminal, where the voltage is fixed. The terminals are defined for those microgrid terminal that are either outputting or absorbing the power into their own merits, which behave as a shellfish terminals. The slack terminals are defined as those DC terminals are actively balancing the power flow in the microgrid. These are the reference points, which behaves as a generous terminal. So, this is the difference between the power terminals and the slack terminals. Slack terminal mainly control the DC microgrid voltages. In order to maintain the power balance, there must be at least one slack terminal, like you have a slack bus and analysis, which within the microgrid for the selfish power terminals are not capable of balancing the power of their own. Now, let us see that this is the control of the microgrid, and we may have as we have seen in case of the AC microgrid also, we have a central control and the autonomous control. This is a central control, everything will be put into the under central control, all the converters, and thus you require a very fast communication channel, and the central controller is a very much overloaded also. So, original idea of the DC microgrid scheme was central control, which stems from the traditional power system control. You have a master controller room, from there you try to control by the SCADA all your power system equipments. So, that is something was thought process while initiation of the DC microgrid, but it has many limitations. Using a central control, the real time sampling and detection are collected from all the terminal, all the data to be fetched and to be processed, and instruction required to send back to the individual converter, and thus you require a very fast communication channel, very fast processors. But those are not a challenge nowadays, but still it will have a network block bottlenecking, and as well as faster action will be revert back, because you please understand that unlike AC microgrid, DC microgrid has to be very fast in operation, because transients are very severe in nature. So, detection, so if the fault has occurred, let us say, and voltage is increasing in case of the AC microgrid, or in case of the, then there is a problem. If voltage itself is decreasing and fault has occurred, so you automatically your current comes down. So, you have a good time to react till it goes to the peak, and thus by that time you should be able to react. But that kind of aspects are naturally does not exist in case of the DC microgrid, and for this reason we require to have a very fast channel of communications. The sampling and the detection are controlled from all the terminal to the general central controller, as illustrated in this figure. So, this is the one converter, they can have inverter converter, you can fetch voltage and current from each of the converter, you process it, check it and send the instruction, everything has to be done by the central control. Now, central control processes and detect the informations and manage the output instant in order to the each terminal. So, there will be a time delay system, because what you get it, you process it, you send it back, that will be a time delay system. So, that is one of the aspect that the researchers can think of. This is a particular example of the microgrid, DC microgrid with a central control is a time delay system. The voltage can typically drop to 0 or rise to the double in few milliseconds in steady state mismatch if it is not addressed. This is the severity. So, we have to keep in mind that it has to act very fast, because in absence of the inductance, inductance does not work because it does not have a frequency, and transient so will be very fast in case of the DC. As a result, extremely high bandwidth and reliable communication channels are demanded in this case. That is what I was narrating. And overall reliability of the central control DC microgrid is generally difficult to guarantee as a failure on the central controller on the communication channel may results in the total collapse. So, if some portion of the microgrid is not feeding a right data, then you may collapse the whole data. If some, so you require to isolate the grid very fast, unlike the AC microgrid, otherwise whole system voltage will collapse. So, that is a few challenges of the centralized control. And for this is we are looking for the autonomous control. So, what happened here, each bus is each microgrid is connected to each bus, and each individually try to maintain the DC bus voltage depending on the slack terminal or the power terminal. So, slack terminal will try to maintain the voltage, and the power terminal, and please understand that this slack terminal and power terminal are interchangeable. Whose like solar maybe at the 12 noon he has a maximum capability, so that can be a slack terminal. And similarly, in evening when actually solar goes out, ultimately you have to depend on the grid, and grid is also at its peak value at a peak price. So, there may be the battery storage will be the slack terminal, and at night maybe when your grid is cheap, then your active rectifier will be the slack terminal, other will be the follower power terminal. So, accordingly it will change. So, thus autonomous control is based on the local detections, and the primary control of the terminal converter can be incorporated in the plug and play. That is one of the user friendly features. You can add or disconnect any controller as you wish, an expandable manner without the need of the communications as illustrated in the figure 2. So, let us discuss the autonomous strategy. For autonomous control, voltage variation based technique can be implemented, which does not needs additional communication channel, but local voltage detections, hence better reliability and the costs. Drop control is normally employed through the throughout the voltage variation based autonomous control scheme. So, that is something we require to also keep in mind, that group control is normally employed throughout the voltage variation based on the autonomous control scheme, and that is also find its lot of advantage and redundancies. Assuming that the voltage difference among these terminals is negligible, because it is a DC bus and it has a very minor, very small resistance, and certain range of operation of the voltage can be set and divided into the number of bands in order to ensure the power balance. Certain combinations of the terminal is assigned to the each band acting as a slack terminal. So, that is something we require to also operation in such a way that in order to ensure the power balance, certain combination of the terminal is assigned as a side bus. So, that is what happened. Let us say solar is healthy and grid is less price, then you make solar and the grid as your slack point, and other required to follow. So, battery may charge or discharge depending on the requirement, but after some time when grid price increases in evening, so maybe you got a plenty of wind, then wind and the battery will take out, and that will be the slack bus, and others required to synchronize. So, for this reason we see that based on the voltage band definition in figure 3 and therefore, the four-stated control criteria, the typical autonomous voltage control schemes can be established and which is demonstrated in this figure. So, there is a voltage band -1, voltage band -1, voltage band 0, voltage band +1, voltage band +2. So, there will be a different kind of voltage band. It may be actually let us say 40 to 52 volt, and you may have a very narrow voltage band, and this is maybe your this voltage is 48 volt, this may be 50, and this may be your 46, and this make it 44. So, this is the range, and so generally what happen, these things happen generally when solar is not there. So, ESS and a load that has to be fed into the combinations. So, you are in a watts voltage band, then you require to control the voltage. Then second is that you are in a negative voltage band 1, then ultimately task of the power balance it will be delivered to the mainly the storage element. Thereafter, in this zone generally there is a little bit of small voltage difference, then a grid side converter will come into the picture depending on the price of the grid. Same thing generally here it will feed power ESS, and in positive band it will take out power. And if you go to this voltage band +2, then you have to curtail the generation. Curtail the generations means you have to ultimately you just referred back here. If you are feeding power to the grid, then you try to increase the power from the grid, and this is the mode of operation, or there is another means to follow. So, that is the autonomous voltage control, and thus let us explain it very fast. The control levels are level 0, the level 0 correspond to the 0 voltage band, where the system is in the normal grid connections, and it is very close to this required voltage level. The DC bus is maintained by the utility grid, by the AC to DC converter or DC to AC converter, and this becomes the slack terminal. And level 1, when you have energy surplus generally, it controls the corresponding voltage in +1 band or -1 band, where the grid fails to regulate the DC bus within the band A, and the energy storage ESS, the slack bus starts taking the responsibility of maintaining the DC bus. Similarly, the level 2 corresponds to the voltage band +2 and the -2, where the grid side converter and the ESS cannot maintain the DC bus voltage within a band A, and an emergency control is performed. That means you may shut down the load in -2, the non-critical load required to be shut it down. So, the leading load shedding is carried out in band 2 and generation curtailment in band 2 plus. So, wind pitch has to be controlled something like that. Note that since load shedding is normally is on and off process, that is also something we require to keep in mind. it cannot possibly maintain the DC bus voltage within a band 2, but it pushes the band back to the -1, and then your previous control technique comes. Thank you for your attention. We shall discuss with our DC microgrid control system in our next class.